Welcome, dear students. Unit-2, 2022, Advanced Mechanics, Semester 6. Question paper 2022, Unit-2, Question 3a. State the Hamilton's principle and derive a Lagrange's equation of motion from it. Hamilton's principle: the motion of a conservative holomorphic dynamical system from time t1 to t2 takes place along such a path that the line integral of the Lagrangian of the system between the limits t1 to t2 is stationary, that is extremum, for the path of the motion. This path is consistent with the constraints, if any. Mathematically, this action integral I equal to integration t1 to t2 Lagrangian of the function q, q dot, t dt. This action integral extremum, that is variation of action integral delta I equal to delta of integration t1 to t2 L dt is equal to 0. Now, the derivation of the Lagrange's equation of motion from the Hamilton's principle. So, this is the D'Alembert principle, and from D'Alembert principle, and for we here discuss the for non-conservative case when force are non-conservative, and this actually this integration 4 is the extended Hamilton's principle, and then from this extended Hamilton principle we finally get this is the Lagrange's equation of motion, and next we derive this conservative system case, force is conservative, then we derive this, but it is a lengthy process, so I prefer is the alternative process is this beginning of the PDF. This Euler-Lagrange's equation, actually this is the Lagrange's equation of motion from the Hamilton principle. Lagrangian L of the system given by L is functions L of Q1, Q2, Qn, Q1 dot, Q2, Qn dot, and T. Qi and Qi dot stand for generalized coordinates and generalized velocities respectively, and T is time. Construct n-dimensional configuration space and varied paths are drawn in it, as the endpoints of all varied paths are coterminous both in coordinates and time. This is the varied path dot dot sign, and this is the actual path. This is the coterminous points 1 and 2. So path coordinates and time are same. So delta integration t1 to 2 to L dt equal to integration t1 to 2 to delta L dt plus integration t1 to L delta t. Actually, this delta dt is equal to 0 because this delta dt, there is no point of varied path including the endpoints this. So we get delta d is equal to integration delta L dt. Now delta L is the summation of I equal to 1 to small n del del qi L delta qi plus summation of I equal to 1 to delta qi dot L delta qi dot plus del del TL delta t, provided all qi dot and t are strictly independent arguments, which is true only for bilateral holomorphic system. Again, the third term on the right hand side, this vanishes as delta t equal to 0. So we can write this summation over del del qi L delta qi summation over I del del qi dot L is ddt of delta qi, because delta q dot, that is delta dqi dt, that is delta and ddt interchange for qi, this here. So we write del del qi delta qi plus ddt of del del qi dot delta qi minus summation over I ddt of del del qi dot L delta qi. So we get this ddt of this minus this, and this plus this is minus, so this is delta I common. So summation ddt of del qi L minus del qi L into delta qi, equation 3. It should be noted that here that although uh, qi and qi dot are all independent of one another, delta qi dot and delta qi are not because of the variational identities delta qi dot equal to ddt of delta qi. Thus, we get by integrating from T1 to T2, delta integration T1 to T2 L dt equal to integration T1 to delta L dt. This is equal to, so delta L equal to this, so integration summation of our del qi delta qi T1 to T, actually this is the ddt, so cancel integration this, so upper limit and lower limit T1 to T2, lower limit T1 T2, and integration T1 to T2 summation of I equal to 1 to n, this dt of del qi L minus del qi L into delta qi dt, equation 4. The first term, the right hand side, this term vanishes because this delta qi at the fixed endpoints 1 and 2, this delta qi are 0. Delta qi for t1 equal to 0 and delta qi for t2 equal to 0. So this integration Hamilton principle states that delta integration t1 to t2 LDT equal to 0. So obviously these terms equal to 0. So we get integration t1 to t2 summation over I ddt of del qi dot L minus del qi L delta qi dt equal to 0. Equation 6. Since QIs are all independent of each other, so delta QI can be arbitrarily, and above equality is satisfied if and only if the derivative of del QI dot L minus del QI L equal to 0 I equal to 1 to n, which are the well-known Euler-Lagrange equation or simply Lagrange equation of motion for any bilateral holomorphic system having no non-potential forces and n degrees of freedom. But you can derive this treatment alternatively, but this is lengthy, and here we more generalized case in forces of non-conservative. So this is the more details and more lengthy part. And here we use the actually extended Hamilton principle, this equation 4, and this GI is the components of the generalized force. This, and ultimately we get this equal to this, and this is the for the non-conservative force. So again for conservative force we derive this case, and this is ultimately we get this expression. This next question 3b, in spherical polar coordinates r theta phi, the Lagrangian of a particle of mass m under the influence of a central potential Vr is given by L m by 2 and this minus Vi. Find the momentum conjugate to the cyclic coordinate. Also find the Rauthian and write down the Rauthian equations of motion. Here the Lagrangian L does not contain phi explicitly. These are r dot, theta dot, but there is no phi here, phi dot. So phi is cyclic coordinate. Here is L. So p phi equal to del phi dot L. This equal to L is this. So with respect to phi dot, actually this term is phi dot. So m by 2 r square sin square theta 2 into phi dot. So we get this conjugate momenta p phi corresponding to cyclic coordinate phi. This constant, we know this. Now Rauthian r is equal to r equal to p phi dot minus L. So p phi into phi dot. So p phi is this and phi dot. So phi dot square stands for theta mr square, and value of L as given in the question this. Support this here. So ultimately we get r Rauthian is equal to expression 1. The Rauthian equation of motion for r and theta, non-cyclic coordinates for r and theta, ddt of del r dot capital R minus del r capital R equal to 0, and ddt of del theta dot r minus del theta r equal to 0, equation 2 and 3. Now, del r capital R equal to this, del r dot capital R equal to this, because capital R equal to this, expression 1. So, we get del theta capital R equal to this, del theta dot capital R equal to this, and using these values in 2 and 3, we get actually from 2, we get this expression 4, and from 3, we get the expression 5. So, 4 and 5 give the required Rauthian equation of the motion. Next question, 3C1. The Lagrangian of a system with 2 degrees of freedom is given by L equal to m x dot y dot plus m bracket x square plus y square. Write down the expression for canonical momentum PR conjugate to R in polar coordinates. And second part, the Lagrangian of a system is given by L equal to half ml square bracket theta dot square plus sine square theta phi dot square minus mgl cos theta, where mgl are constants, so that phi dot sine square theta is conserved. Question 3C1. Here, put x equal to r cos theta and y equal to r sin theta, and convert to the Cartesian to polar, cylindrical polar. This is the two-dimensional motion, so this is the polar coordinate. X square plus y square equal to r square. Difference with respect to t, this x dot equal to r dot cos theta, dot means ddt, minus r theta dot sin theta, and y dot equal to r dot sin theta plus r theta dot cos theta. So x dot into y dot equal to this, we get this half of r dot square minus r square theta square sin 2 theta plus r dot theta dot cos 2 theta. Hence the Lagrangian L in terms of r and theta, we get this L equal to m x dot y dot plus m x square plus y square. So x square plus y is equal to r square, and x dot y dot equal to this expression. So in terms of r and theta, we get this expression 1 is the in terms of L and theta. Now del r dot del r dot L equal to this, and PR equal to del r dot L. So in the question, write down the expression for the canonical momentum PR conjugate to R. So first find this, and PR equal to this, and this is the required expression for PR conjugate momentum PR corresponding to R. Next question, part 2, is L is this given by this, and so that phi dot sine square theta is conserved. So L equal to this, here theta dot, but no phi here. So phi actually here cyclic coordinate in L. So for this cyclic coordinate, p phi equal to del phi dot L, and this equal to m L square phi dot sine square theta, if this is 1. And p phi the conjugate momenta corresponding to phi. And the Lagrangian equation of motion is ddt of del phi dot L minus del phi L equal to 0. So, and ddt of p phi equal to del phi L, this is equal to 0. This del phi L equal to 0 because phi is cyclic coordinate in L. So, p phi equal to constant. Now, p phi equal to this ml square phi dot sine square theta. So, this is equal to constant kc. Then phi dot sine square theta equal to k by ml square. Now, m and l are both constants. So, k by ml square is new constant k dash. So, obviously, phi dot sine square theta is also constant. So, this comes out here. Next question, D. If for a certain mechanical system H equal to p square q square minus lambda pq, where lambda is a real constant, then show that pq is a constant of motion. Obtain the Hamilton's equation of motion for a simple pendulum. Now Hamiltonian H equal to p square q square minus lambda pq. Hamilton's canonical equation of motion is given by q dot del del ph, p dot minus del del qh. So del del ph, so with respect to p, partially with respect to twice p q square minus lambda q, and p dot equal to minus 2p p square q with respect to q, so twice q here, so 2p square q plus lambda p. Now ddt of pq is equal to p dot q plus pq dot. So value of p dot is this and value of q dot is this from 2. After simplification we get this. So pq equal to constant. So pq is a constant of motion. We show that pq is a constant of motion. Second part, obtain the Hamilton's equation of motion for simple pendulum. Now at this simple pendulum, this p point, this is p point, kinetic energy T equal to half m s dot square. This is equal to L into theta. This is the string length L and this is the angle theta. So obviously this arc length S equals to L into theta, and half mv square. Mv square is dot is the here velocity. Actually this is the speed, this square, half m L square theta dot square. And the potential energy is mg into O into Q. This is the ground level, the base level is this O. So this height, vertical height is the OQ, is the distance. So mg distance, and this above the base level. So this plus this mg OS minus OQ, QS. From this right angle triangle, this SPQ and this SP OQS, QS by SP, this base by hypotenuse, this is equal to cos theta. So from this L minus L cos theta equal to this. So V equal to mgl 1 minus cos theta. Since the system is conservative, so H Hamiltonian is the kinetic energy plus potential energy, is T plus V, is equal to T equal to this and V equal to this, and L equal to T minus V, is T minus V. Generalist moment of P corresponding to theta here is equal to P equal to del del theta dot L, we know that. So del del theta dot L is this, so just with theta dot, so this half ml square twice theta dot, so this ml square theta dot. Then HP theta equal to this m half ml square, this value of theta dot is the p by ml square whole square plus mgl 1 minus cos theta. So this is the H, this is the total energy E. The Hamilton's canonical equation of motions, this theta dot equal to del del P capital H. So with respect to P, partially with respect to P, we get half into 2P by ml square, P by ml square, and P dot equal to minus del del theta H. So these are the Hamilton's canonical equation of motion, theta dot and P dot equal to this. Next question 3E. Define action of a mechanical system so that if a coordinate corresponding to a rotation is cyclic, the system remains invariant under such coordinate rotation and angular momentum is conserved. Action integral, this I integration t1 to t2 L dt, and the L is the Lagrangian t minus v, is known as the action integral. Now this theorem is this: if coordinate corresponding to a rotation about an axis is cyclic, the system remains invariant under such a coordinate rotation. That is, the Lagrangian is invariant under the rotation about this axis of rotation. and the conjugate angular momentum is conserved. Now, Lagrange's equation motion for generalized coordinate qk, derivative of del L qk dot L minus del L qk L equal to 0, where L equal to T minus V, this is the kinetic energy, V is the potential energy. We consider a conservative system so that V is not a function of velocities, qk dot. V is a function of qk only, and T is not a function of position qk. Then del L qk dot V equal to 0 and del L qk T equal to 0. Then equation 1 can be written as this ddt of del L qk dot T plus del L qk V equal to 0, because del L qk means T minus V. This del L qk T is 0, so we have to this minus del L qk V, and from this del L T minus V, so del L qk T is, and del L T minus V, V is not function of qk dot, so del V del qk dot equal to 0, so we get ultimately this. And pk equal to del L qk dot T, so ddt of pk equal to this gk. This gk actually minus del qk V, this gk, and qk, actually qk is the theta, represents the rotational coordinate, and the generalized force gk is the component of the total applied torque tau vector about the axis of rotation, and the generalized momentum pk is the component of the total angular momentum capital J vector about the same axis. So this is the pk dot equal to gk, this expression. Actually the Lagrangian equation of motion reduces to here this pk dot equal to gk, where pk is the component of the total angular momentum capital J vector about the axis of rotation, and gk is the component of the total applied torque tau vector about the axis of rotation. Now gk equal to summation over the fi vector dot del L qk ri vector I equal to 1 to capital N. Capital N is the number of particles in the system, and fi vector and ri vector is the applied force and the position vector of the ith particle, and capital N is the number of particles of the system. Let us consider an arbitrary infinitesimal rotation delta theta. Actually theta represents this qk delta theta of the system about the z-axis, axis of rotation. Say the position vector ri vector due to the rotation delta theta will change by ri vector plus delta ri, where delta ri vector equal to delta theta z cap is the unit vector in the z-axis cross ri vector. This is the picture diagram. This is the OJ, the axis z-axis, and this is the point P. This OP is the RI vector, position vector, and this angle with the z-axis, this phi angle, and this point P dash, and this OP dash is equal to RI vector plus delta RI vector. And so from this right angle angle, we get RI sin phi actually. So this arc length PP dash equal to this delta Ri vector. Actually, this is the Ri sin phi delta theta. This actually this is the length of this arc length is delta Ri. Now Z cap cross Ri means the mode of Z mode of Ri into angle between the Z and Ri is sin phi. So obviously we get Ri sin phi into delta theta. Phi is the angle between the OP and OZ, and Z gives the unit vector along the axis of rotation Z. So del L qk Ri vector equal to Z cap cross Ri. So this actually delta theta equal to qk. So from this we get this delta Ri vector equal to delta theta Z cap cross Ri vector. From 4, this the gk, the generalized component of the generalized force gk, component of the tau along about the torque about the axis of rotation. Tau is the torque about the axis of rotation, total applied force torque. So gk equal to this, and this interchanging the dot and cross z cap dot ri vector cross fi. and this z cap is independent of summation. So z cap dot summation of r is ri vector cross fi vector, and this the ri cross fi is the tau y vector. This is the for ith particle, and this tau y, the total torque. This capital tau is the total torque for the whole system. This total applied torque, and this z cap. So tau z is the component of the torque along the z axis. Now pk equal to del del qk dot t. So this equal to summation over mi vi dot del del qk ri vector, and this equal to mi vi into del del ri qk, actually qk is theta. So del is equal to z cap ri vector. Z cap is in root of summation. This capital pi vector is the mi into pi, actually the ith particle, linear momentum of the ith particle, and this is equal to z cap, and the summation of a capital gi vector. This capital gi is the angular momentum for the ith particle. The summation of this capital G vector is the capital Gz is the component, of the total angular momentum capital G along the z axis. From 3 using 6 and 7, from 3 actually this pk dot equal to gk from 3 using 6 and 7, we are able to get this capital jz dot equal to tau z, and this represents the equation of motion about the axis of rotation. Now if the rotation coordinate qp is cyclic, it will not appear Lagrangian or v, and we hence gk equal to minus del del qk v equal to 0. Then 3 becomes pk dot equal to gk equal to 0, and jz dot tau z equal to 0. Hence derivative of jz equal to 0 and jz equal to constant. Actually this jz is the theorem of angular momentum. The absence of component of the applied torque along this the axis, the corresponding component of the angular momentum along the same axis is conserved here. Hence the given theorem is proved. Note that due to space isotropic space, the change in the Lagrangian L of the system for an infinitesimal rotation must be 0. That is delta L this equal to 0. No change in L here. Actually L is invariant in this case. Thank you for watching this video, and the PDF of this note is given in the description box.